So today my session is on building AI clusters, what network engineers need to know. This topic is a little bit networking adjacent, but I hope that the audience here still finds it interesting. So if for those of you that follow the latest on AI, it can feel a little bit like drinking from a fire hose, and it's easy to get lost in all the jargon and buzzwords. My talk today is aimed at giving you a better understanding of GPU clusters, the underlying infrastructure for AI training and inference. So the objective for today's sessions is, number one, to share a framework so that you can understand functionally what's happening in GPU clusters. And secondly, to share some key details on how the underlying network fabric is designed and built. So let's dig into the key building blocks of an AI cluster. And that's starting from top to bottom here with programming frameworks. So you'll see there's a number of prominent programming languages that are leveraged here. Things like PyTorch and TensorFlow are two of the biggest, but you'll also see tools like DeepSpeed and Ray consumed. Then the next layer down is really coming to cross-GPU operations. And this is really facilitating this is coordinating the exchange of data between GPUs. So within this, you'll have these collective communication libraries, things like Nickel from NVIDIA, RICL from AMD. And it really enables the complexity of the underlying distributed infrastructure to be abstracted away. The next layer beneath that is what's happening in terms of networking within a node. And so here you have a number of proprietary techniques. In NVIDIA, this will be things like NVLink, NVSwitch, and in AMD, this will be things like Infinity Fabric. As we move down to the next layer of networking across nodes, this will probably look a little bit more familiar to the audience here. This is things like InfiniBand. Traditionally, this has been the way that networking has been done between GPUs and storage. But more and more these days, people look to turn to Ethernet, which is when we have Rocky V2, which is much of what I'll speak about today. And also looking forward, this is a UEC or Ultra Ethernet Consortium. And then in terms of the actual workloads running on the GPUs, this is facilitated by things like CUDA in NVIDIA and ROCm on AMD. And then you actually have the raw hardware accelerators themselves beneath it. Familiar products like H100, B100, GB200, and so on for NVIDIA, or this could be like a MI250, MI300 for AMD. So just taking a little bit more of a look at the programming languages themselves. So I showed some of the different options on the previous slide, but the whole idea here is to provide some kind of simplified control over neural network architectures, their loss function, the optimization algorithms, and enable them to do this with minimal code. So on the top right-hand side of this slide, you can see just a simple example neural network. You'll always have this input layer, you have an output layer, and you have many, many hidden layers within it. Could be hundreds, could be thousands, and this results in a lot of matrix maths within them. So these programming languages allow the underlying complexity of the hardware to be hidden away, and for them to just to kind of speak easily with these neural networks. You have built-in support through these languages for everything that you need for distributed training, so things like scalability across multiple GPUs and nodes, cross-GPU communication and how you optimize that, and also the different flavors of data and model parallelism. And then on the bottom right, I have a bit of a pseudocode example there with PyTorch. The key thing that I want to call out here is, through these higher level programming languages, you have some control over the lower layer. So you see the Nickel layer there. So you can kind of tune, tweak, and optimize how you use Nickel directly there, which brings me on to the following slide. So there are several fundamental techniques to pipeline data processing across a GPU cluster. Quick refresher about what we're actually doing through this training process of a neural network. So basically, during each training phase, we pass data through the neural network, and each GPU makes a prediction. And a gradient matrix is calculated based upon how far off this prediction is from the actual result. So with that, let's look at the first kind of pipelining technique, and that's data parallelism. So in this particular case, we take our training data set and we actually batch this to run across multiple different GPUs. So in this example, just 4 GPUs. The same neural network is running on each of these 4 GPUs. What we do is we pass that data set through the neural network, and it gets passed through each of the, all the matrix multiplication takes place using the weights of the model. And then as an output, we calculate a gradient matrix for each of these. Now, the challenge here is that you've got this gradient matrix that exists on 4 different GPUs. They're all different. We need to find a way to combine this together. And this is where the network starts to become relevant. So basically, we have this communication collective called all reduce there. What's done in that case is each GPU sends its gradient matrix to all other GPUs. You perform an average function, and then you broadcast that back to all other GPUs. And then from there, what we do is we actually back propagate that matrix backwards through the neural network, and we can actually tune the weights a little bit. And so every iteration here, we get a better and better fit of the neural network to the training data. The second technique is something called pipeline or model parallelism. So in this particular case, maybe you have a neural network that is too big to fit on any one given GPU. So in this particular example, I've got 4 GPUs. So maybe the first quarter of the neural network layers are on the first GPU, the second quarter on the second, and so on and so forth. And what we leverage here is a communication collective called send and receive. So basically, this is a point-to-point operation between one sender and one receiver. And in this way, we can send the results directly from one GPU to the next GPU in the stream. So same process happens here from a training perspective. We pass that data set through, it cascades through all the different weights, and we calculate a gradient along the way. And when we get to the final one, then essentially we do the same thing in reverse. We back propagate the calculated gradient, and we update the model weights along the way. And the third technique is something called tensor parallelism. So in this particular case, we need to do some matrix math. So it's something simple, matrix A times B, and you get a result C. But for some reason, I might actually want to spread the processing of this across multiple GPUs. So what I can actually do here is I can do partial processing of that operation on 4 different GPUs. So I take the matrix A, but I'm just kind of multiplying out by a given column in matrix B. And so I get the result on at the end there, but it's only a partial result. So I need to find some way to actually combine things together. And so this is where we use this all gather collective. And basically, this is every GPU sending its matrix results to all other GPUs. And in this way, we can recombine and get the result of matrix C and have that present on every GPU. So if you start to put these things together, as is commonly the case in kind of large-scale LLM training, you'll actually employ multiple of these techniques all at once. So I can use tensor parallelism together with pipeline parallelism, and then also with data parallelism. And I think that the key underlying message that I want to bring across here is to actually do this, you can see that there are meaningful demands on the network in terms of the all gather, send, receive, and all reduce collectives to actually facilitate the communication required across this GPU fabric. So if you start to put this together, you can actually see that, iteratively what is happening in this process is you have this computation phase on each of the respective GPUs. You have this communication phase where I need to send all my partial results out to, the other relevant GPUs. And then there's a synchronized phase here. Basically, each of those operations needs to complete, and only then across my GPU cluster can I actually create the next, do the next compute step. So the net of this is my cluster can actually only progress as fast as the slowest link or the misbehaving link within the overall cluster. So how does this actually look from a traffic pattern perspective across the network? So, if you look at the top right-hand chart here, this is something that you might think of as quite familiar from a traditional data center environment. You have some type of data center utilization that kind of ebbs and flows depending on the consumption or the use of the application. Conversely, if you look at the bottom right-hand corner, this is what the traffic pattern is going to look like within a GPU training environment. And so what you see is a really pulsating traffic flow there. So basically, every time you have this communicate phase, there's a sharp, high bandwidth pulse across the network fabric, and then you have nothing, because essentially that's where the compute phase is actually taking place. And this process repeats itself over and over. And suffice to say, it's a very different traffic pattern. It is also quite a different type of network that you need to engineer to actually work nicely in this environment. So in practice within a cluster, how does this actually look? So basically you have, as I mentioned, this library like Nickel. It actually sets up the GPU to GPU topology over which these collectives take place. And so Nickel is going to consider both the intra and inter-server communication. So in this particular example, I've basically just taken 2 GPU servers, each one of them with 8 GPUs there. And you basically see a ring topology that's being created there. And I have like a switch, which is labeled rail 0, which is connecting these 2 rings. And essentially what I do there, or what we've done there, is we've created one large ring that's actually interconnecting these 2 GPUs. And so what you see is each stage in the pipeline there is flowing across this topology that's been created by Nickel, and that's how we actually stage up and sequence all the different tasks within the cluster. So if you start to look at this, you need to think that we're putting, Nickel is actually putting together a topology that's, across the internal interfaces of the server. So in NVIDIA, this could be, NVLink, NVSwitch. In the case of AMD, this could be Infinity Fabric. From a network perspective, so between the NIC and those rail switches, you need to have Rocky V2 in this particular example, and that's to facilitate RDMA memory transfers that are basically happening there, in this example, between GPU 0 on server 1 and GPU 0 on server 2. This is a simple case. You could also have multiple rings that are set up in parallel, but there's also tree structures and whatnot that may be set up there. So, and this can all result in slightly different traffic patterns across the network. So let's move on to the physical infrastructure of a cluster. And this brings me to the concept of building modular data centers or modular clusters, and you need to introduce the concept of a SU, or scalable unit, also known as a stripe. So the idea here is that each SU is a self-contained mini cluster that's been pre-validated at line rate across compute, storage, and network, right? The reason for this is it gives operators a repeatable power and thermal envelope and rack layout that they can continue to apply as they scale out their cluster. From a networking point of view, this is about having a repeatable cabling, routing design. Instead of software versions, you'll all be fixed per SU. And then one of the things you'll also see is that there's an optimal node count there per scalable unit, and this is linked to the GPU server's NIC count and the leaf switch radix. Okay. And so as you want to scale out your cluster more from there, you'll basically lay out additional SUs, and then it's really about the network architecture that enables you to do this, and there's different options for how you might scale that out. Now, a couple of comments on an SU. So this can vary from GPU to GPU, server to server, operator to operator. I want to give a few examples of this here. So in this particular case, we've got an SU with 256 B200 GPUs. The servers are air-cooled, and we've got 1 rack of networking. You see overall this SU is consuming 9 racks. However, I could also have an SU that is also 256 B200 GPUs, but I'm using liquid-cooled GPUs. And in aggregate, this is only consuming 5 racks. Why this might be relevant is perhaps this more condensed or compact footprint, it might enable me to use shorter reach optics or maybe even copper DAC cables, which can help me to optimize the overall cost of these clusters. And then last example, you can also look towards some of these rack scale systems that NVIDIA has. So things like NVL72, and in this example using GB200. And SU in this case might be 576 GPUs, each with liquid cooled, and that's going to take up 10 racks. So I just mean to say that the actual footprint of each of these SUs can vary from operator to operator, GPU type to type, and so on and so forth. So with that, let's start to step into the networking a little bit more. And I think the first thing that you should observe is that there's not just one network fabric associated with a cluster. There's actually multiple functional parts to this. So at least functionally, you'll have the concept of a back-end GPU network, a storage network, an in-band network, and an out-of-band management network. And then we'll also have a secure DCI as well. So let's talk about some of the kind of functional attributes of those different fabrics. And the first part I want to talk about is the backend and storage networks. I'm going to focus on Ethernet here. And actually, this is really the main part of the cluster design that I'm going to focus on for the rest of the presentation. So firstly, for this to be deployed in Ethernet, it requires a higher profile Ethernet in order to support these specialized AI workloads. And this is because primarily it's RDMA-based traffic that's running over these clusters. The networks need to support lossless Ethernet. So this is Rocky V2 today. Yep. And then what you'll also see is that there'll be some specialized topologies that are utilized here to reduce latency. And I'll speak about that in a few slides' time. There should typically be no oversubscription in this environment. And then from a technology point of view, in the backend network, we do see this evolving from Rocky V2 into UEC or Ultra Ethernet in the coming years. The in-band network, also known as a front-end network, is always deployed using Ethernet. So typically, this might be orchestrating some of your training workloads, and you'll also use it for serving inference traffic, so north-south stuff towards users. It's a very traditional cross fabric that you might use here, so very similar or common for anyone who's deployed regular data center fabrics. Oversubscription is quite typical in this space. And then one optimization, it's not uncommon for in-band and storage networks to be combined together for GPU as a service providers. And lastly, the kind of data center interconnect network, if you have data center clusters and data center environments spanning multiple sites, typically you'll have some kind of wide area network, which implies a different set of technologies required there. So let's step in a little bit more here and talk about RDMA. This is really the central workload that's running in these GPU and storage networks. So the important thing about RDMA is it facilitates low latency, high throughput transfers over the network between GPUs with low CPU overhead. And there's two key attributes that enable this. It's this attribute of zero copy data transfers and kernel bypass. So if you take the particular example I've shown here on the left-hand side, you can have some type of AI training application that is able to write directly into the GPU memory there. And when that is ready to kind of send to the remote side, you can immediately send that out and directly from that GPU memory to a remote GPU's memory without any other intermediate memory copies there. The way that it does this over a Rocky V2 transport. If you look at Rocky V2, what is it from a network perspective? It's basically InfiniBand, wrapped around with UDP and IP. Few key attributes there. You have things like a flow being identified by a Q-pair ID, and then it also relies upon a lossless fabric. I mean, in short, if you look at the retransmit or kind of windowing mechanism for RDMA, it relies upon timeouts and retransmit there if you have lost packet. It's really bad. You really don't want that. So lossless Ethernet is a must. So how do we actually enable lossless Ethernet on the network? Well, really, there's two key attributes that I want to call out today. So the first attribute is something called ECN, or explicit congestion notification. So ECN kicks in when there is mild congestion somewhere in the network, and it provides a way to signal to endpoints to slow down rather than to drop packets. And so if I just take an example here, so I've got some type of flow going between this GPU 1 in zone 2, and it's sending to GPU 1 in zone 1. And in this particular case, we start to have some mild congestion between super spine 1 and spine 1. And in this case, what we actually start to do from superspine 1, because this congestion has been detected, we actually start to set the ECN bits within the IP header. And then the receiver on GPU 1 can actually send a notification over to the sender GPU to say, hey, there's some congestion happening here. And in response to that, it will actually slow down the transmission of data. And when it does that, then that congestion on the link between superspine 1 and spine 1 will be alleviated, and the network will go back into a steady state. The second key attribute is something called PFC, or priority flow control. So PFC is intended to kick in when there is severe congestion somewhere in the network, so things like microbursts and whatnot. And this is an explicit signal to adjacent switches or NICs to temporarily stop sending packets for a specific QoS class, so a switch's buffer is not exhausted. So in this particular example, this same link here between superspine switch 1 and spine 1 is experiencing some extreme congestion. And so in this particular case, that superspine 1 will actually generate a PFC pause frame. So this is going to be received by spine 1 and spine 2. In this case, it may cause the ingress buffers of spine 1 and spine 2 to also exceed a threshold, so it may actually propagate this onto downstream devices as well. And when that extreme congestion is alleviated and goes away, then these pause frames will stop being sent and the network goes back into a steady state. Okay, so I mentioned earlier about there being some specific topologies relevant to these GPU backends. And I think there's two main topologies that I want to introduce today, and the first one is a rail-only fabric. And the crux of this is that it enables all GPUs to reach all other GPUs within one hop. And then we can reduce the latency between those GPUs. And the crux of this is that for every given server there, you basically have this relationship between GPU 0, NIC 0, will connect into rail 0, so a dedicated Ethernet switch. And similarly, GPU 1 and NIC 1 will connect to rail 1, and so on and so forth. And you're left with a topology that looks like what I have in the top right-hand corner there. Now, for this to work, it's dependent on some GPU-specific features. In NVIDIA world, this is a feature called PXN. And so basically, each node's local NV switch connectivity is used first to move traffic to the same rail as the destination GPU, and then it sends it over that rail so that you don't need to cross rails. So for example, if I need to go from GPU 0 on server 0 to GPU 1 on server 1, I'm first going to send it internally towards NIC 1 on server 0, then over that rail 1, and then it's going to get to my destination there. The scale of this design is bounded by the rail switch radix. So for example, if I have a 64-port 800 gig switch, then this can connect up to 128 GPUs, each with a 400 gig NIC attach. If I kind of spray this out, overall, I can scale this out to around 1,000 GPUs, and this implies that I'm using 8 of those 64-port 800 gig switches. Now, if you need to scale beyond this, then you need to look beyond this particular topology, and that's where we turn towards a rail-optimized topology. So for this one, basically, what the networking that you have within an SU is identical to what I just described then with rail only. The key difference is I'm going to reserve half my uplinks on these rail switches to connect to some higher tier within my topology there. And this is basically, introducing a spine tier here. And basically, we can organize these spine switches into zones, and that's going to connect to each of the respective rails. The net of this is that all GPUs within a zone can be reached within 3 hops. I still have no oversubscription, and then a single zone can support up to 8,000 GPUs. And if I need to go bigger than that, well, I need to introduce one more tier, which is basically my core switches. And we organize those into planes to connect into the different spines. The result or the outcome here is that all GPUs in the cluster can be reached within 5 hops. There's similarly no oversubscription, and spines within a zone will need to connect with equal bandwidth to all planes. And this design can scale up to around 262,000 GPUs. And if you've got a cluster that big, then you're doing really well. The next question might be, how do I actually physically connect all of this stuff together? And this is a really important thing because this can have a dramatic impact on the overall cost of building these clusters. And the way I've organized this is basically just looking at optics in terms of the reach. So from left to right, I've got a few copper options with DAC cables and whatnot. And then from there, we move into optical pluggables. And then I've also organized it in terms of what's relevant for switch-to-switch connections and switch to NIC. Thank you. So in general, if you look towards the optimal way to be able to connect your NICs and the rails, the most cost-effective option, if you can, is to use copper. But this is fundamentally distance limited. And so depending on the size of your SU, you may or may not be able to accommodate this. If the reach is not enough, then your de facto option moves towards these SR optics, which will give you in the order of 50 to 100 meters. So that would be your go-to option for NICs to rail. And similarly for medium-sized clusters, this can work just fine for rail to spine and spine to core. Now for really large clusters, you need to look at reach beyond 50 or 100 meters. And then you move into these DR optics, which will give you up to 500 meters of reach. And then lastly, if you have a cluster that's actually spanning across multiple data centers on a single campus, then you need to look towards these FR optics, which will give you up to 2 kilometers. Okay, your cluster starts to become really big at this stage, so you probably want to think about how you actually do health monitoring here. As said, if you have issues on certain links there, this is going to impact training across the entire cluster. So common health metrics that we have operators monitoring is CPU, memory, traffic counters, your ECN stats, PFC, and also your queue depth as well. We advocate for gRPC-based telemetry, so you can push this out of the box as fast as possible. And then also from a multi-tenancy point of view, which is relevant in a GPU as a service environment, you probably want a way to visualize and show those resources on a per tenant basis. Okay, the last part that I want to talk about here is the storage network itself. So storage is a critical part of these AI clusters. It has a couple of key functions that I want to call out. So namely training data ingest and also periodic checkpoints in case you have failures there and you need to resume from this. So just a point on checkpointing, for example, your general rule of thumb is that as your GPU cluster becomes larger, then the probability of a failure becomes higher. You can see a little bit that chart on the bottom left-hand corner, which basically shows a growing cluster size and the mean time to failure coming down. The result of this is if you have a failure, you basically, everything's going to stop and you need to revert back to that last checkpoint to resume from there. So the more frequent you can actually do checkpointing here, the less disruption to your service, to your training process you're actually going to have. How this actually looks from a network point of view is for each of those SUs that I described earlier, there'll be dedicated storage leafs for that. And then you'll also have these kind of high-performance NVMe clusters you see on the right-hand side there. You similarly have storage leafs there, and you'll have some type of fabric interconnecting the two. As you look to the design of these storage fabrics, there's 2 predominant deployment models. Number 1 is to have a dedicated storage network. This aligns to the NVIDIA reference architecture. It's a more performance-optimized cluster design. In general, it still relies upon lossless Ethernet there. And you have dedicated storage NICs and storage leaf and spine switches as well. And the second option is to basically have a shared in-band and storage fabric. So this is a design adopted by many neoclouds or GPU as a service companies. It's a bit more cost optimized. You still need lossless Ethernet here, but you need to dimension it around both the storage traffic as well as the in-band workloads. And in this case, you typically need some kind of overlay support there to deal with some segregation of the kind of front end and storage workloads. On the right-hand side, you get a view there on how you actually dimension the storage network. So typically, if you look towards NVIDIA, they have a good way to view this. So basically, they'll talk about your requirements in terms of good, better, and best. Good is for natural language processing, so this could be text data that you're pulling into the cluster. Better is going to be image processing with compressed images, and best will be if you're doing training based upon 1080p or 4K or uncompressed images. And what you see there is that this actually maps into a sustained read and write data rate that you need to have for every given GPU in the cluster. And if you look at that red box that I have there, this just takes what are the requirements for a given node. So this is a single node with 8 GPUs. If you look across to the best side there, that maps to like a sustained read rate of 320 gigs and a sustained write rate of 160 gigs. Put all that together, this is what your network topology looks like. It's a much more standard CLOS topology. Spine with storage leaves on the left-hand side, feeding into spines. And if your cluster becomes really big, also cores as well. And then on the right-hand side, that's where my NVMe appliances are. So, are we there yet? I know the timekeeper is asking me that. So this is the last slide that I have. So basically just a bit of a look forward to what we see coming next. This is basically Ultra Ethernet. So Ultra Ethernet is trying to take a modern RDMA optimized transport layer, or trying to build a modern RDMA transport layer for AI and HPC workloads. It's all building upon Ethernet. It's kind of standardized across NICs, switches, optics, cables, and software vendors. And so there's some advanced congestion control capabilities there. Basically, what I described earlier for Rocky V2 will eventually evolve into Ultra Ethernet. The other key thing to mention is that there's work done within Linux libraries, libfab, to actually ensure that this can be directly consumed by Nickel and Rickel and whatnot. Last comment, the UEC 1.0 spec is out now, so you'll probably start to see vendors showing interop and demos of this over the next 6 to 12 months. With that, thanks a lot.